Hi, we are Natalia and Andrea, and we're going to present the two chapters of our book of thermodynamics. That are chapter 4 and chapter 5. So the first topic is moving boundaries. So first we have a quasi-equilibrium process in which it's a mechanical work, and usually it's automobile engines that they either auto-compress, or they auto-expand. So in this we have the system that it remains in equilibrium the whole time, and we have this formula that is going to be the integral of work B, that is going to be equal to the force times the distance, that is going to be equal to the pressure times the area in the different distance, and then we have the remaining equation is going to be P times the differential of B. So in this, P represents the absolute pressure, and dV is the volume change, depending if it's compressive or expanding. It's going to have a different sign. It's going to be positive when it's expansion, and it's going to be negative whenever it's compressing. So the total boundary work that we're going to denote it, WB, it's the integral of the pressure times the differential of B from 1 to 2. That's going to be the difference of volume. And we can represent it graphically in a PV diagram like this one, in which it's going to change depending on the process path. So the total area beneath our diagram is going to be the same as the work being done in magnitude, and the work is a path, so we can also represent it with the area as well. That's going to be the differential depending on the area difference that we have in this equation. It's going to behave different depending on the process that it's going to be done. And the relationship between the pressure and the volume is given by the experimental data. So instead of doing it like with experiments over and over again, we could just calculate the area beneath the graph. And we can generalize the boundary work with the equation that we gave before, that it's going to be the work P, that is work boundary, of the integral of P times the differential of volumes. So now the energy balance of a closed system, as we know, it's going to be the energy out minus, energy in minus the energy out is going to be the difference of energy within our system. And if it's per unit mass, we're going to denote it with the little e, like the small cap, not the capital letter, the other one. And it's going to be as the same, the E in minus the E out is going to be the E difference in our system. And for a closed system that is undergoing in a cycle, we're going to have the work net, that is the work out, the work in minus the work out. It's going to be equal to the Q net, that is also the differential. And we put the little dot whenever it's over a period of time. And then we're going to talk about specific heats. That in specific heat is a property that helps us compare energy storage capabilities of various substances, and is the energy we require to rise the temperature 1 degree per unit mass of a substance whenever the pressure is maintained constant, or the volume. And the Cp is the energy required to do the same as the pressure is maintained constant, and the Cv is whenever is the volume maintained constant. And we consider it with a fixed mass in a stationary closed system in a constant volume and pressure. In here we have another way of denotating the Cv and the Cp. For example, the Cv in here is going to be the internal energy, the difference of internal energy within a difference of of temperature, and in here the enthalpy in a difference of temperature, the Cv. And internal energy enthalpy and specific heat of an ideal gases. So in here we know that the enthalpy and the internal energy are only dependent of the temperature in this case. So therefore we're given the U, the H, the Cv, and the Cp. For an ideal gas, they have fixed values, like they don't change, and we can find them in our tables. And the change in internal energy or enthalpy for an ideal gas during a process from state 1 to state 2 is going to be the difference of internal energy is going to be equal to the CVT of the integral from 1 to 2, that is the different states, and then we can denote it like this in another way, that it's going to be temperature, final temperature minus the temperature 1. And for the Cv, it's going to be the difference of enthalpy that is going to be equal to the integral of the Cp of the temperature. And we can also denote it with the difference of enthalpy. It's going to be equal to the Cp, that is a fixed value and a fixed value, times the temperature difference. And internal energy enthalpy and specific heat of solids and liquids. Solids and liquids are denoted as incompressible substances. So they have the Cv, the Cp is equal to C only because it's a fixed value for them because it's not going to change.
So now I'm going to talk about chapter 5, which is mass and energy analysis of control volumes. So in this type of systems, control volumes, we have that mass can cross along the boundaries, so we have to take into account the mass flow rate, which is given by this formula, which is the mass flow rate equals the density times the average velocity times the cross-sectional area. So, and there are going to be some cases which we are going to have the volume flow rate, and the volume flow rate equals the velocity times the cross-sectional area, and these two equations are related by this equation. And this states that mass flow rate equals the velocity, the volume flow rate over the specific volume. So now we have to take into account the conservation of mass principle, and for these systems we have that the mass is constant in the control volumes. So the total mass flow rate equals that is going in equals the total mass flow rate that is going out. And for single stream, which is the ones that only have an inlet and an outlet, it's the mass flow rate that is going in equals the mass flow rate that is going out, and then we can write it as the density times the velocity times the area. And for the case of liquids, which liquids are incompressible flows, we are going to have the volume flow rate, and this is the same as the mass flow rate. And for single streams, we are going to have the same, the volume flow rate equals the velocity times the area. But because there is no conservation of volume principle, there are some cases that we're not going, the volume flow rate that is going in are not going to be the same as the volume flow rate that is going out. This is the case for the air compressor, but for the other cases we're going to say and that the volume flow rate remain nearly constant. And now for flow work and the energy of a flowing fluid. The flow work is the work necessary for maintaining a flow, continuous flow. So for this, in this case, the fluid upstream forces the fluid element to enter the control volume. So we can imagine that there is an imaginary piston. So the force equals the pressure and times the area, and we know that the work flow equals the force times the distance that it's going to that it needs to cross to get to the control volume. So we can say that the workflow equals the pressure times the volume. And for calculating the total energy of a flowing fluid, we have to take into account another term, that is the flow energy. So we are going to add it to the energy. So we have the PV plus the internal energy, plus the kinetic energy, and plus the potential energy. But we know that PV plus the internal energy equals the enthalpy. So we're going to have this equation. This is the kinetic energy, and this is the potential energy, and C equals the difference in elevation. And this helps us because if we have the enthalpy, we don't need to calculate the flow work. And for energy transport, we can multiply this times the mass, and we obtain it. And when in some, like in most cases, we're going to have the kinetic energy and potential energy are going to be zero. So we're going to only have the mass and the enthalpy. And we can state that fluid properties can change from point to point, but in the general system, they are going to be the same. And therefore, the mass, volume, and energy can remain constant, and the boundary work is zero. And heat and work interactions between the system and the surroundings do not change neither. And we're going to have that for the energy balance, the total energy that is going in equals the total energy that is going out. And for single stream devices, we can say that the kinetic and potential energy are going to be zero. So we're only left with this equation, that is the heat minus the work equals the difference in enthalpies. So we're going to have different systems. In this case, there's the nozzles and the diffusers. So in the nozzle, we have that the area, this area this area is bigger than this. So the velocity 2 is going to increase. And for the diffuser, it's the other way around. So it increases the pressure of a fluid by slowing it down. And in these type of systems, we're saying that the heat, the work, and the potential energy equal zero. So we're going to only focus on the kinetic energy. And there's some other systems like the turbines and compressors. So in these types of systems, a fluid passes through the blades. So the blades are going to move and they produce work. And we're going to say that heat transfer and potential energy are negligible, and kinetic energy as well. And for the mixing chambers, we're going to have two fluids, and they're going to mix. And the heat, work, and kinetic energy and potential energy are also negligible. And we're only left with the total energies of the strings. And there's the heat exchangers. So in these types of systems, there is a fluid going in and another fluid going in, but these fluids doesn't combine. They're only exchanging heat, and heat is transferred from hot to the cold one. And in these systems, there are no work interactions, and neither kinetic and potential energies.
In the steady flow processes, we have a change in the control volume. So like we can compare it a lot with a steady flow process in which we have a control volume that is fixed. But in this case, there are changes in the boundaries. So we're gonna have two types of energy: the boundary work, and also the process being done inside the system. It also has energy, and we have to take that into account. So in this case, it's gonna be under a finite time period. Like we're gonna measure the energy depending on the time. We have some examples that is rigid vessel, discharging fluid from a pressurized vessel and a gas, or a turbine with pressurized air. And they are fixed in shape and size. We have to assume they are stationary because of the moving boundaries. And we have a difference of mass. It's going to be the mass in and the mass out. It's going to be our mass inside the system. So here is what I was saying, that our energy total is going to be the energy content of the control volume, so the process that is going to be inside the control volume, and also the energies that is going to happen in the inlet or in the outlets. We have an idealization in these cases, and we're going to assume that it's a fluid flow at any inlet or an outlet. This is what I was saying before, also that of the idealization over the cross section of an inlet. Energy. So this is the equation we have, in which it's gonna be the heat, that it's the heat net, so it's the difference of heat that is going in and out, and also in the work, and then where it's gonna be equal to the mass changing of the out minus the in, and it's gonna be equal times the mass times the difference of mass, well, it's enthalpy, the difference of enthalpy, that is the mass times the internal energy. And that's all. Thank you. Bye.